It's my pleasure to quickly introduce Professor Michael Beaney, who's a professor of philosophy both here at the Humboldt University in Berlin and also at King's College London. He's a specialist particularly of analytical philosophy and the history of philosophy, and will present to us today 5 case studies where we get to know creativity in different subject domains. And what I find quite striking about these case studies is that they also include strong cases of development of logic, and that might also include mathematics. And I think that's really a treasure for us, because that gives us an opportunity to bring together the HPI as an institute for software systems engineering and the kind of creativity that may be happening in these places traditionally, and design thinking that we're so interested in. So we might encounter some connecting principles that we could potentially explore further. And we've been in touch for about a year by now, or a little more. And the reason would be to bring together 2 worlds of theory, or the intention was that we are, of course, having a lot of practical experiences in design thinking, and one could look even further where other people, as we are so collaborative and try to bring perspectives together, what other theories about creativity and innovation there are. And philosophers traditionally develop very, well, straightforward and precise accounts. So that's always quite interesting and challenging, and there's probably a lot to bring together. And for those who are interested, Mike also is in the process of building up a group of people who study creativity, particularly in the history of philosophers, well, with a very deep look into these processes and these principles across different phases in history, right? Mm-hmm. Yeah, so thank you for being here.
Okay. So thank you, Julia. Thank you, Rush, and thanks for the invitation. So, okay, well, I'll try to keep it to 45 minutes. There's actually far more in my PowerPoint slides than I can really go through, but they're partly there so that if you wanted to follow up some of the ideas, you can do so. And also, if there's particular things that you want to ask about in the discussion, we can perhaps go back to them. So I'll try and keep it to the. Does that work? That timer? Why don't you put the timer on, then I'll make sure. Good. Very good. That's great. Then I'll try and keep to 45 minutes. Good. Okay. Right. So here's the plan. So just a few words of introduction, and I'll say something about my interest in creativity and the philosophy of creativity. And then, as Julia said, I want to take 5 case studies right across the history of philosophy. Though, as Julia said, and Ulrich said, I have a particular interest in analytic philosophy, so I'm being particularly interested in the creativity in analytic philosophy. And then I'll just really say a few words to draw some conclusions from that. So that's the plan. These 5 case studies, Plato, Kant, and then 3 from analytic philosophy. Okay, so introduction. So creativity or creative is not actually a word that one finds used a great deal in discussing philosophy, especially analytic philosophy. And so I've been concerned with why. That said, sometimes analytic philosophy is modeled on science, and we recognize that there's a great deal of creativity in science. One obvious example is the role that thought experiments play. And Einstein is a good example of someone who's extremely creative in coming up with thought experiments to come up with his with his scientific ideas. And if you think about that, there are, in fact, a number of different ways in which philosophy is creative. Perhaps the most obvious is what I call scenario imagination, which doesn't just include thought experiments. But one thing that philosophers are very good at is trying to come up with weird examples, scenarios, case studies to test our concepts. And that is actually an important part of philosophy. Also, philosophers, particularly analytic philosophy, use analysis. I'll say something about that in a minute, and synthesis. And finally, I think there's actually, when one thinks about it, a lot of creativity involved in simply presenting, running through arguments, as I put it there, finding the right expression, or right way of explaining things. You need to find exactly the right word or offer the right kind of argument to develop your point. So there's lots of different ways in which philosophy can be regarded as creative. Now, what I'm going to focus on is analysis, and I have done quite a lot of work on the history of conceptions of analysis. And I think there's some widespread myths about analysis. In particular, I think the biggest myth is that by analysis we simply mean what I call decomposition. Analysis means breaking something down into its bits. Okay, here's a famous example of that idea in Schiller when he's criticizing an analysis. He compares the philosopher to the analytical chemist. The philosopher could only discover how things are combined by analysing them, only lay bare the workings of spontaneous nature by subjecting them to the torment of his own techniques. So it looks rather dry and boring if analysis just means breaking something down into its parts. And in fact, when one looks at what's called analysis or looks at particular methods and practices of analysis, one finds other conceptions in place. And in particular, what I've called the regressive conception of analysis and the interpretive conception. The regressive conception just means you're trying to identify the basic principles or axioms of a system in order to then explain something or perhaps draw some more conclusions. And that can actually be quite a creative thing, to find the right axioms and principles. And then there's also what I call interpretive analysis, which I'll explain in a minute. It's what I particularly see as characteristic of analytic philosophy. And there, I want to say there is an element of creativity involved. In particular, what I call conceptual creativity. So one thing that philosophers do is shape, forge, develop new concepts to solve problems. You often need to make distinctions to solve problems. And that's really what I think philosophers are particularly good at. But they don't often recognize that that's quite what's involved. They tend to think it's perhaps not something that's important to understand in itself. So here's two quotes from people who do accept that philosophy is essentially creative, conceptually creative. And there's a quote from Nietzsche: philosophers must no longer accept concepts as a gift. Somehow they're just there waiting in a heaven to pull down, nor merely purify and polish them, but first make and create them, present them and make them convincing. And then there's this quote from Deleuze and Guattari, what in their first chapter, What is Philosophy? Philosophy is the art of forming, inventing, and fabricating concepts. Philosophy is the discipline that involves creating concepts. Concepts are not waiting for us ready-made like heavenly bodies. So, on my view, philosophy really is a conceptually creative discipline. And in my own work, I'm wanting to try and understand what exactly is involved in that. Okay, that's just an introduction. So just a few more words about the philosophy of creativity, which I suppose is what I'm interested in. Now, often this has been seen as part of aesthetics, as part of the philosophy of art. Who are the creative people? They're really artists, aren't they? But in fact, in philosophy as well, there's been concern with the nature of scientific discovery. Paradigm shifts, post-Kuhn, we're well aware of the idea of paradigm shifts. So there's an area where one might also talk about creativity. So for me, the philosophy of creativity should bring together debates in aesthetics about creativity with debates in the philosophy of science about scientific discovery and so on. But in particular, what I'm concerned about is philosophy. And there's actually been surprisingly little written about the creativity of philosophy. Now, I won't go into this in detail. There's a good question. Why is that the case? And I think part of it is to do with this distinction that's quite important, or has become important in analytic philosophy. It dates back to Kant, but it's particularly important from the late 19th century. This distinction between genesis and justification. One says, look, how an idea arose is of no relevance to the philosopher. The philosopher just wants arguments, wants justification, right? Finding good arguments for something. So the question about how an idea was created, how it arose, is then pushed into the background. That's something maybe historians or someone else can investigate, but not philosophers. And I think that distinction is actually problematic, though that won't be the topic of my talk today. Well, here's the famous account of genius that Kant provides. I put it here, and this is in the German, where he thinks of genius as a talent to, if you like, create a new rule that no one's thought about or could have anticipated before. Okay, and it's a rule that somehow the genius is able to do by how I often put it is by sort of tapping in to some common understanding that we might have. Okay, so you think of a great artist, it might take a while for this to be manifest, but the great artist is someone who produces something that maybe over a more or less short or long period of time, other people can say, "Oh wow, that's really interesting," and something unusual and new. Okay. That characterization applied to philosophy, I think, also holds. If you want a description of what genius is on this Kantian conception as applied to that might make it relevant to philosophy, here's a possibility. Genius is the talent to find exactly the right expression to communicate something that strikes a chord in others or crystallizes their own thinking. I think we'll keep that definition, if you like, that characterization in mind as we explore some of the case studies. Okay, and here's again a nice quote from Alexander Pope, an essay on criticism, which sort of captures the idea here as well. True wit, so that's the genius, is nature to advantage dressed, what oft was thought, but ne'er so well expressed. Something whose truth convinced at sight we find, that gives us back the image of our mind. So I think part of what it is to be creative or to be a genius, to be a good philosopher, is to often to find the right way to put something, a way that such other people can say, "Oh yeah, that's exactly right." It crystallizes thinking in their own minds. And I think that also has to be recognized as an important part of philosophy. Okay, one more preliminary description before I turn to the case studies. So I've been quite influenced by the work of Margaret Bowden, who I think for anyone interested in creativity and design thinking, especially in its relation to computers, I think her work is fantastic. Her book, The Creative Mind, first came out in 1990 as a second edition in 2004. She distinguishes three conceptions of creativity, which I'll explain in a minute, and then she's applied that idea to art as well. And what I'm really doing is seeing how that distinction can be applied to the case of philosophy. So a little bit more about her key ideas, and these will play a role in what I go on to say. So she distinguishes three main forms of creativity. Combinational creativity, which is the sort of perhaps the naive, usual conception of creativity. Creativity means putting new things together and constructing something else. So you come up with the idea of a unicorn by bringing together the idea of a horse and the idea of a horn, and then you get the idea of a unicorn. But that, says she, and I think I agree, is not really the interesting one. The interesting one, or interesting two, are what she calls exploratory and transformational creativity, and they rely on the key notion of a conceptual space, or perhaps in a more broader conception, what she calls a generative system. And essentially, exploratory creativity involves exploring that conceptual space or generative system, and transformational creativity involves changing the conceptual system. And she's interested in how that works. So for her, a conceptual system is a domain of thinking that's governed by a set of rules and principles that determine what cannot be done within it. She alternatively defines it in relation to a generative system, the generative system that underlies that domain and defines a certain range of possibilities. So chess, molecular structures, jazz melodies, these are all examples of generative systems that are governed by a certain set of principles. Okay? So with that conception in mind, you can either explore the potentialities of that conceptual space, okay, seeing what you can do within these constraints, or maybe you can drop or change one of the constraints and develop a new conceptual space or generative system. Okay, and what she's interested in particularly is radical originality, which is what is at the heart of transformational, when you do transform a conceptual space. And what she's partly interested in is being able to model this computationally. If you can so capture a particular conceptual space, and obviously chess is a good example that can be played by computers and now better than human beings. You can model the system, right? But having modeled the system, you can then play around with the constraints, with the axioms, the rules that govern the system, and see what you come up with. Okay, so her thought is that computational psychology can actually help us understand creative transformational creativity in this way. Okay, so for example, I mean, a good example she raises, say, with Euclidean geometry, various axioms that govern Euclidean geometry, you drop the famous parallels postulate and you can develop non-Euclidean geometry. Or you have in music, you have the home key constraint, and you abandon that and you can get non-classical music, atonal music or something. So the idea is you can define your conceptual space, okay, in such a way that then you can make sense of changes that occur when one of those key principles is dropped or negated. Okay, so let's turn to the case studies then. So divided into two parts. Firstly, classic examples in Plato and then in Kant, and one could perhaps see them. One is involving one can call seeing as or aspect perception, and the other what I want to call conceiving as. And then we'll talk about some examples from analytic philosophy. So Meno, Meno's paradox. This goes back to, I think, one of the most important dialogues in Plato's corpus, the Meno, where Plato takes an example from geometry to think about questions in philosophy. And I actually do think, in terms of the development of history of philosophy, some of the most revolutionary moments, the key creative moments in philosophy, have arisen when either mathematics has been applied or methodology has been thought about, reflected on. Plato, Kant, Husserl, Frege. I mean, there's lots of examples where it's developments in mathematics that have partly motivated philosophical changes. Okay, in the Meno, there's this famous paradox, which basically is very simple to state. Either you know something or you don't. Right? If you already know something, then there's no point looking for it. If you don't know something, you won't recognize it when you come across it. So there's no point looking for anything. That looks like obviously something wrong here. Okay, and as an attempt to answer that general question, there's this famous case which I'm sure some of you have heard of, where Socrates asks for a slave boy to come in, and purely, supposedly, by asking the slave boy questions, gets the slave boy to solve a geometrical problem. The idea being somehow that the resources are in the slave boy himself to solve the problem, if only the right questions are asked to get the answers out. But I actually have in a sense, this is a slightly new perspective on Meno's paradox. And it struck me when I was teaching this that something interesting is going on here. So that's why I'm using it as a nice example here. So this is the problem that the Socrates tries to get the slave boy to solve. So the question is, how can you create a square with twice the area of a given square? So you have a square A, B, C, D, and the question is, how can we construct a square of twice the area? Okay. And initially the slave boy says, well, you just need to double the side. Right? So then Socrates gets them to draw it in the sand and says, look, okay, you double the size, and we draw this diagram. What is the area? And then, of course, the slave boy can see that the area is 4 times the size of the square and not twice. So that doesn't work. And then the slave boy thinks, well, then surely halfway between. Okay? And then you draw a square again, and you realize that that's 9. That's what a unit squares, if you like, rather than 4. Rather than 8, which it should be if it's double 4. So that worked. That doesn't count. And then, and this is where sometimes one talks about a leading question, Socrates said, well, what about if you take the diagonal of the square? Okay, there. And then, of course, you can construct a square on that diagonal. And now you can see that that square, okay, has twice the area of this. Okay? And the idea is supposedly that it's only the slave boy has been brought to realize this for himself, rather than that Socrates has told him, though that's one of the issues that's controversial. But what struck me when thinking about this is that what's really gone on in solving the problem is a kind of aspect switch. So the famous case of aspect switch, if you haven't come across it before, is there's the duck rabbit. you can see something that looks like a duck, and it also, I don't know if I can draw it, I don't know to draw it. I should have had one. An aspect switch is where you see something one way and then you can suddenly see it another way. So the famous example is the duck rabbit, which you see, one occasion you see it as duck, and then you may or may not be able to switch and see it as a rabbit. So in this case, it struck me that what was going on was switching from seeing this square as made up of 4 units, 4 squares, right, to seeing it as made up of 2 triangles. Okay, so part of the sort of recognition of the solution to the problem is a switch from seeing it from as made up of 4 squares to seeing it as made up of 2 triangles. Because once you've done that, you can then construct the square on that diagonal and hence solve the problem. So this was the idea that there's often in geometrical problem solving, there's something like this goes on. You have to see a figure in a new way in order to solve a problem. I don't have to see it as made up of 4 squares, I can see it as made up of 2 diagonals, and then I can bring in my knowledge of diagonals in order to solve a given problem. And lots of other examples could be given of that kind of thing, but it seemed to me quite a simple one. Okay, so that's, as I say, if you like, the creative moment. So what I'm trying to understand in these cases really is the moment at which the new conception or the solution to a problem arose. What was the key moment? Okay, and in this particular case, one way at least of conceiving the key moment was to say it involves an aspect switch, a switch from seeing it as made up of 4 squares to seeing it as made up of 2 diagonals. Okay. Now, what's interesting about that kind of case, this aspect perception, is that it sort of solves the Meno's problem as well. How can we learn something? Either you know it, in which case you're not going to know it already, in which case you don't learn anything, or we know nothing at all. It seems to me what goes on in aspect perception is there's something there to look at, but you're seeing a pattern, okay, that's there to be seen, but it hasn't struck you. Okay, and I think that's quite an important element in creativity, that there's the features are there, but we just haven't seen it in a certain way. Perhaps we need to see a relation between one figure and another figure in order to reconceive the figure in order to solve a particular problem. So there's a sense in which the learning is recollection. The slave boy has to himself go through this process. He has to see that you can change from seeing it as made up of 2 squares to seeing it as made up of seeing it's made up of 4 squares to seeing it's made up of 2 triangles. Okay, as I say, if anyone wants to ask questions about this, we can discuss it further in discussion. So let's move on to one of the other kind of key moments in the history of philosophy, Kant's so-called Copernican Revolution. And Kant's major work is the Critique of Pure Reason, 1781, and he himself talks about a Copernican revolution. And this is the idea that we can cognize of things a priori only what we ourselves have put into them. So let me just, very, as briefly as I can, just explain the key idea here, because here also there's a kind of switch from seeing things one way, conceiving things one way, to seeing things another way. A bit like the Copernican Revolution, right? You switch from seeing the sun is going around the Earth to seeing the Earth is going around the sun. There's a sudden switch that enables you to make progress. So here's the passage. There's a handout. Oh no, if there's a I gave Julia the PowerPoint slides, so you can circulate them if you like. So it's in German as well, but here's the English version. Kant says, up to now it's been assumed that all our cognition must conform to the objects, but all attempts to find out something about them a priori through concepts that would extend our cognition have on this presupposition come to nothing. Hence, let us once try whether we do not get further with the problems of metaphysics by assuming that the concepts must conform to our cognition, which would agree better with the requested possibility of an a priori cognition of them, which is to establish something about objects before they're given to us. This would be just like the first thoughts of Copernicus, who, when he did not make good progress in the explanation of the celestial motions, if he assumed that the entire celestial host revolves around the observer, tried to see if he might not have greater success if he made the observer revolve and left the stars at rest. So that's Kant's own description of the revolution that he achieved, and he himself compares it to the Copernican Revolution, where there's a sort of switch from seeing things one way to seeing things another way. So what precisely is that way? Well, partly it's motivated, and maybe I won't go through the details of the motivation here, partly motivated by problems that David Hume, another philosopher, had about causation. But basically, Kant's key idea was we're trying to understand how we have knowledge of the world, in particular of necessary connections between things, which we can't just read off from the world. Right? We can read particular things, but not that there's a necessary connection between them. Nor is it that if we have knowledge of one thing, in itself, that gives an account of how something necessarily follows. That happens in mathematics, but not in the empirical world. Okay. So what Kant then think, this is his Copernican Revolution, he says to himself, well, maybe we have to see in some sense, we have to think in some sense of us imposing a certain structure, the structure of causal connection, on the objects. We're reading certain things into the world. Okay? So instead of always thinking, well, look, our knowledge is determined by how things are in the world, and we're just somehow passive, maybe we should start thinking that how the world as we perceive it is partly constituted by our own categories and structures and so on. Okay? So the thought was we impose on the world as we receive it certain fundamental structures, one of them being that there's a connection, if you like, between cause and effect. Okay? And that's actually a very, very important idea, that if you like, the world to some extent is constituted by us and not merely as a nature in itself. There's a lot to say about that, but that was the essence of Kant's Copernican Revolution, that there are certain fundamental structures, concepts that we use to structure our experience. And part of the task of philosophy then is to try and articulate those structures. Okay, and a really powerful, important idea in the history of philosophy. And that was his Copernican Revolution. So there's a sort of switch here from seeing things one way, thinking that knowledge, your account of knowledge must be in terms of how the things supposedly given to you through your senses impact on you, versus recognizing that there's a contribution from our minds in structuring the world. Okay. So as I put it there, we don't simply passively receive impressions, sense impressions, but actively give them form and synthesize them through the concepts of our understanding. So the very idea of a concept then is transformed. Okay, concepts are not just abstracted from the world, but are also, at least the fundamental categories, things that in the sense, if you like, they're kind of like innate, that we impose on the world in having the experiences that we do. So if you like, this was a very powerful idea and was certainly important in Romanticism, that creativity then is built into the very nature of conceptualization. Right? That we're kind of, and there's a sense in which we structure the world as we experience it. Okay. That's all too brief, but I hope it gives you some idea of the Copernican Revolution. Okay, so let me turn then, in the last 20 minutes, okay, we can't do them all, to three more case studies. I'll probably focus on the first one, because that's, in a sense, the interesting one. That's, and probably doesn't involve less existing knowledge of philosophy. Okay, so three case studies: Cantor, Frege, and Russell. So, Cantor, Gail Cantor. So there's a nice way to motivate this. As often in philosophy, it's paradoxes that sort of drive philosophical thinking. So here's a very simple paradox. Okay, so you consider two infinite sets: 1, 2, 3, 4, 5, the set of natural numbers, and the set of square numbers: 1, 4, 9, 16, 25. This is called Galileo's paradox. Which set is bigger? Who thinks the first set is bigger? No one? Who thinks the second one is bigger? One tentative hand. Who thinks they're the same? Okay, why are they the same?
They're both infinite, I would say, and then the amount is
Okay, they're both infinite. Okay. But, well, that's good. Okay, they're both infinite. Right, that suggests there's a single notion of infinity, and they both just have that number. Anyone else? Another different account of why they're the same? That's one account. I mean, wouldn't one say, well, look, hold on a minute. This one contains all of these, right, and more, right? You've got 1, 4, right? All of those, this set is contained in that set, right? And there's more, so surely this one's bigger. Why not?
Well, whichever index you are in the first set,
Yep.
you could just go to the same index in the other set. You
Right.
would have one.
Good. Okay, yeah. So there's a sort of 1-1 correlation, right? All along. Okay, now what's significant about this is, if you like, there are 2 criteria for 2 sets having the same number of members or not, right? Here are the 2 criteria, right? One, that neither is bigger than the other, in the sense of bigger than, for which a set is always bigger than any proper subset. So one often says that that's a proper subset of that. Okay, namely in precisely the sense that all of that set is contained in that, and there's others, right? So in that sense, this set is bigger, because this is a proper subset of that one. That's one criterion, okay? The other criterion is the 1-1 correlation, right? For every member of the first set, there's a member of the second set, and vice versa, all along. Now, in finite cases, those 2 criteria will come together. They'll give the same result. But when you consider infinite cases, those criteria come apart, and we then have to make a decision as to which is the important criterion that we want to hold to. And what Cantor did is he said it's the second one that's the important one. Okay? And then, on the basis of that, he developed transfinite arithmetic. Now, this is, I think, a really interesting case, because there's an important, I mean, this is a good model for what goes on in philosophy generally. When you think about our concepts will often have multiple criteria that come together in normal cases, but then maybe when they extend out, those criteria come apart. So another very ordinary example, say the concept of a person. What is a person? Well, it's a human being, someone who has consciousness, someone that has moral responsibility, someone that feels pain, etc. Okay, a number of different criteria, we would say, for what it is to be a person. Well, now you consider fetuses or people in the vegetative state, and now you ask yourself, are they persons or not? Okay, maybe they feel pain, maybe they're still conscious, but is that what it is for them to be a person? Maybe they're not quite a person in the full-blooded sense, right? So these abnormal cases make you start to think about what really is a person, okay? And you might decide that maybe moral responsibility or self-consciousness is the mark of a person or not. You might have arguments about that. But the point is, you have a concept that has a number of different criteria that in normal cases come together, but when you consider abnormal cases, and this is exactly what the philosopher does, they're very good at thinking of abnormal cases, okay? You then think, which is the appropriate concept? Okay, and what will typically happen? You say, okay, so let's restrict person as having these criteria, and the other is something else. So perhaps we want to distinguish between being a person and being a moral agent, or being a person and being a human being, or whatever. We have to make finer conceptual distinctions when we consider these normal cases. So there you have creativity built, I think, into the very nature of philosophical reflection. Okay, and we often need sharper distinctions to capture and to resolve those problems. Now, on the basis of this particular example, again, if you're not familiar with this, is very quickly run through it. How do we get to transfinite numbers? Okay, so we have the thought that the set of natural numbers and the set of square numbers are the same, have the same number of members, because there's a 1-1 correlation. So now we ask the question, well, what about the set of natural numbers, 1, 2, 3, 4, and the set of rational numbers, including all the fractions? Do they have the same number of members or not? Again, you might think, the set of fractions, doesn't that include all the natural numbers and more? It's got 1, 2, 3, 4, 5, but it's also got 1.5, 1 2/3, 1 3/4, etc. Isn't there sort of 2 times infinity, as it were? Right? Well, here's a little very interesting proof again, what's interesting about this is the diagrammatic nature of it to represent the idea. You draw a two-dimensional array, okay? 1, 1, 1, 2, 1, 3, 2, 1, like that. And you can see that every fraction is on that table somewhere, right? That represents all the fractions, positive fractions. Okay. Well, now what we need to show that there's a 1-1 correlation, if we're going to establish that they have the same number of members, is just an ordering. So we start with 1, down to 2, we go down, up, down, all the way like that, following the black lines, following the arrows, right? So we're correlating the fractional, the rational numbers with the natural numbers. Of course, some we get to twice, so we just have a rule where we move on to the next one. The red ones just drop out if we've had them already. It's a very simple rule, right? So here's a rule of ordering the natural numbers with the rational numbers. So the set of natural numbers has the same number of members as the set of rational numbers. Sounds slightly wacky, but if you keep to the 1-1 correlation as the criteria for two sets having the same number of members, that's the result you get. Okay? Now, what about the next question? The set of real numbers, so that includes the irrational numbers as well as the rational numbers, does that have the same number of members as the natural numbers? Okay? And here, what Cantor did, and this is his famous argument, he said, okay, so assume that we've correlated the natural numbers 1-to-1 with the real numbers. So here's an example. 1 is correlated with 0.1, blah, 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 blah. 2 is correlated with 0.31, etc. Okay? You're putting the real numbers in decimal form, and it'll be an infinite decimal. Okay? So let's assume, ex hypothesis, that you've ordered all the real numbers, if they're going to have the same number of members as one another. Okay? Then Cantor said, hey, we can construct a new number not on the list that's different from every number on the list. So we take the first number, we take the first digit of the first number and add 1. The second digit of the second number and add 1, all the way along. So we get 1.454 all the way along. That number will differ from every single number on the list by at least one place. Right? So we've constructed another real number not on the list. An ex hypothesis, we supposedly had a correlation 1-to-1 between the natural numbers and the real numbers. So there's actually more real numbers than there are natural numbers. So we thought there was just one notion of infinity, right? But what Cantor has shown is that there's more than one notion of infinity, and he talked about transfinite. Okay? So he called the cardinality, the number of the natural numbers, Aleph 0, using the Hebrew letter, and then the next number is Aleph 1, which is the number of the real numbers, and he showed a way of generating a series of transfinite numbers. Okay? This strikes me as extraordinarily creative, conceptually creative, right? Philosophically, I think there's always been problems in the notion of infinity, but Cantor's come along and said, look, let's stick to one criteria of what it is for two sets, even infinite sets, to have the same number of members, and then he's constructed transfinite arithmetic on the basis of that. So here we have conceptual creativity. And the general moral is, under pressure, we have a concept that gives rise to certain problems, paradoxes. To resolve those paradoxes, we have to be more precise about what the concepts are. We solve the paradox, and we also get more sophisticated concepts. That seems to me a good model for what happens in philosophy, especially analytic philosophy. We have these problems, and we have to resolve them by making finer, more careful distinctions. Okay? And here we have a particular model of what goes on, namely, we try to analyze the concept into its constituent criteria, and then try and work out which one we want to adhere to. Now, there may be different ways we can go. Perhaps we could develop an alternative mathematics by taking the other criterion and so on. There may be different ways. So one thing the historian does is often go back into the history of philosophy and say, oh, okay, so philosophers or mathematicians went this way, but there was the possibility of going this other way. And maybe we can go back and discover a new way of proceeding. So that's also quite important. That we can, if we properly understand the process, we can actually be creative as well ourselves by recognizing other possibilities. Okay, so that's the main example I wanted to say. We are sort of running a bit through that, but I think that makes my key point about philosophy being motivated, powered, if you like, by concern with paradoxes and the need to make conceptual distinctions. Okay, so that's the 2 points. Paradoxes are a driving force, and they in turn often prompt us to distinguish the various criteria for the use of concepts, and hence to develop more sophisticated concepts accordingly. So philosophical analysis is conceptually creative. Okay, so I'll just very briefly go over these other two examples, and I can say more if anyone's interested. Frege, Gottlob Frege, is the founder of modern quantification logic, so very important in logic generally, and also one of the founders of analytic philosophy. And his new logic, quantification logic, which he was the first person to develop, was first presented in his Begriftsschrift of 1879. What's crucial, as we now see it, in the development of quantificational logic, is the conception of concepts as functions. You represent concepts. You analyze sentences involving expressions for concepts in function argument terms. So what Frege did is he took function argument analysis from mathematics and applied it to the analysis of sentences, and hence was able to develop logic. As I say, I certainly can't try and explain the details in 2 minutes. But underlying that is this idea, and in some ways it's just an analogy, that concepts are functions. And I've argued, as I've written probably too much about Frege, I've argued that in many ways his whole philosophy arises from thinking through the implications of this underlying conception, that concepts can be seen as functions. It gives rise to various of his problems. But it is ultimately only metaphor, an analogy. And when we get problems in Frege's philosophy, as we do, one needs to say, well, hold on, so how did we get to the position where these problems arise? We have to go back and say, well, do they arise from thinking of concepts as functions? So on the one hand, I think using analogy and metaphor is amazingly creative, enables us to do all sorts of things. On the other hand, it can sometimes be confusing. Further down the line, there may be problems arising. And then we need to, as it were, go back and uncover, if you like, the creative step in order to sort out where went right and where went wrong. Okay, so that's also an important part of the philosopher's task, to try and identify those key moments, and sometimes the way in which a particular metaphor played a role in the development of the philosophical ideas. Okay, so that's maybe all our quick say about Frege. So one thing I'll say about Russell, and then I'll try to conclude. So this I just want to get at one of the key ideas in analytic philosophy. A very, very simple example. We had Meno's paradox. Here's a very simple example. Take the sentence, unicorns do not exist. Very simple sentence. Seems to be true. Unicorns do not exist, right? Now, it's tempting to think, well, how can we give an account of that sentence? One treats it as a subject-predicate sentence. There are unicorns, and the unicorns have this property of non-existing, of not existing, right? Simple decomposition analysis. But then you say, well, hold on a minute. What are these unicorns that don't exist? How can we refer to them? Looks rather puzzling, right? There seems to be something misleading about unicorns do not exist. It's not the same as saying Donald Trump is a buffoon, okay? We understand what that means. So Donald Trump refers to a particular person. We're saying that he has a certain property. We can make sense of it. But we're not, when we say unicorns do not exist, we're not saying, look, there are these unicorns, right, and have this property of non-existence. That looks rather weird, right? So what's really going on when we talk about unicorns do not exist? Well, Frege and Russell and analytic philosophers said, well, what we're really talking about is not unicorns because they don't exist. We're talking about the concept of a unicorn. And we're saying the concept of a unicorn does not have instances. Okay? So to solve the potential problems that give rise to, in trying to analyze unicorns do not exist, we say, hey, what it looks as if it's saying is not what it's really saying. And we're saying what it's really saying is the concept unicorn does not exist. The concept unicorn has no instances. Now, if you know some logic, okay, then that's readily formalized in the predicate calculus in quantification logic, which Frege developed, right? There's not the case that there's something which is a unicorn. And to put it in more sophisticated terms, again, if you're not familiar with this, it doesn't matter. The idea should be, the basic idea is just what's important. What we're saying then is, when we say unicorns do not exist, we're not making a claim about certain kinds of objects in the world and attributing a property to them. Rather, we're saying something about concepts and saying something about those concepts. So the idea is there's objects and there's concepts, and the concepts you could say things about. In other words, the concepts fall under second level concepts. So a claim about unicorns, the claim that unicorns do not exist, is analysed not as saying that an object falls under a first level concept, does not exist, rather that the first level concept unicorn does not fall within the second level concept is instantiated. In other words, there's a different logical relation involved when we talk about unicorns not exist. Now, how does this relate to analytic philosophy? Well, essentially, doing this kind of thing is reinterpreting the sentence to make clear, to resolve the philosophical problem. Right? If there's puzzles about what it is to claim that something doesn't exist, they're resolved by saying, hey, you're not talking about objects, but about concepts. And you can say things legitimately about concepts, namely that they are not instantiated. Now, to do all that also involves bringing in a number of different concepts and distinctions. So you need to draw a distinction between first level concepts and second level concepts and so on and so on. Okay? So all this conceptual creativity is, as it were, invoked, is developed in order to resolve these kinds of philosophical problems. And I call that interpretive analysis because the problems are solved by interpreting the sentence in another way. And for me, the useful analogy here, and some of you will be familiar with analytic, with geometry, with analytic geometry. The useful analogy is between analytic philosophy and analytic geometry. So how is analytic geometry analytic? Well, what happens in analytic geometry is that you translate the problems of geometry into the language of arithmetic and algebra. You represent a line as y equals ax plus b, for example. Then you solve them and you can translate them back into geometry. Okay? So it's analytic because it reinterprets the problems in a different form, and you can use the resources of that conceptual system to solve the problems. Okay? So too in logic, in analytic philosophy, you reinterpret problematic sentences in a way that resolves the philosophical problems. Okay. So that's yeah. So here's the idea. Interpretive analysis reconceives problematic statements, shows what they're really about, and in the process of doing that, you introduce a battery of further concepts to make sense of that process. So it's extraordinarily creative. You're solving problems, yes, but you're doing so precisely by making some concepts more precise, by introducing more sophisticated concepts and so on. Good. So final section then. Yeah. So let's just quickly go back to the distinction between exploratory and transformation. Just a couple more slides. Just to see what's going on here. A number of different cases here. I think one can make use of Margaret Bowden's interest in the distinction between exploratory and transformational creativity. In terms of the exploratory aspect, I think when you're trying to solve geometrical problems, you may need to do all sorts of exploring of the possibilities of the conceptual system. Once Cantor had made this Copernican shift, he then needed to explore the full range of possibilities of doing that. And so too within analytic philosophy, Frege and Cantor develops transfinite theory. Frege and Russell develop analytic philosophy. So there's exploratory elements there that are also important. But what I was particularly interested in was the transformation bit. What was the bit that really was the creative moment? So, in the case of the Meno's paradox, the slave boy makes this aspect switch, changing from seeing the squares made up of 4 unit squares to seeing it as made up of 2 diagonals. The Kant's Copernican switch comes from seeing that there's a sense in which we contribute to the experience that we have of the world, rather than just thinking of it as we're just passively receiving things. Cantor's theory of transfinite numbers arose by dropping one of the 2 criteria. The others maybe I haven't properly explained to fully make sense of. Okay, so final slide then. I'm teaching at the Humboldt University, so every morning I go into the Hauptgebäude, and of course, what do you see there? You see this famous quote from Marx: Die Philosophen haben die Welt nur verschieden interpretiert, es kommt aber darauf an, sie zu verändern. And it always irritates me whenever I go in to the Hauptgebäude to see that right across the hallway. It seems to me terribly misleading, because interpretation itself makes changes. Marx himself is a counterexample to his own claim, right? His philosophy changed things enormously. It seems to me that the very act of interpretation is a form of changing things, okay? And that's precisely what I've been concerned with in my own work in looking at interpretive analysis. It involves creativity and changes our way of seeing things. So here's my own improvement, my creative improvement on Marx's quote. Die Philosophen haben die Welt immer verschieden interpretiert, deshalb haben wir das Mittel, sie zu verbessern. And the other thing you know, if you've been into the Hauptgebäude, is that you have this so-called artwork, right? That just says Vorsicht Stufe as you go all the way up the stairs. So my take on that is mind the step, as we'd say in English, but in this case the step would be mind the step of creativity. So on that note I will end.
So thank you very much. And before we move over to an open discussion, I would like to take the opportunity for a quick reflection. And I'm sorry, my slides will be very primitive. There have been just a couple of minutes to create bridges between these very intense case studies full of details. And my attempt would be to maybe look at the principles that you've conveyed to us and how they relate to design thinking. So let's see how this may work. Just very few slides.
Do you want any time on the clock?
Maybe 10 minutes. Okay, so this is one of the slides that I just recapitulate, and I highlighted this seeing as. In a couple of case studies, you've talked about seeing as and the principle of interpreting a subject domain. And I would like to just bring up this familiar representation of the design thinking process, and in particular, this point of view phase. And I submit to you that this is really a phase where we look at a problem and we see it as something. We see it as something, and the question is, do we see it in a conventional way, in a way that the problem has always been looked at, or do we see it in a novel way? And quite often, I believe we have the experience that coming up with a novel problem view is actually the door towards novel solutions. And I haven't placed this on a slide, but you talked also about exploratory and transformational creativity, and that could also be a notion for us to take a closer look at. And we might consider thinking about the ideation phase, where we explore whatever conceptual space we have. So we have a particular understanding of the problem, and that opens the door to particular kinds of solutions. So we explore these solutions that are given to us once we have adopted a particular problem view. Whereas in the point of view phase, we have the potential for transformational creativity in the sense that we may tap a completely novel problem view, and that opens up doors that maybe people have not opened before. So that's just a notion that we might want to explore. And then also this concept of what it means to analyze, that of course you're an expert in. And the question, what are we actually doing when we are looking at subject domains, when we synthesize our findings? And I believe in the history of design thinking theory, there have also been discussions about that, what we are actually doing. And they were not so clear, not as clear as you are with your notion of analysis as being something that can be per se creative once it comes to the interpretation part. So just to recapitulate that from the design thinking pioneer John Arnold, he would say analytic thinking analytic thinking is a major part of creative processes. Analytical thinking detects the features and structure of an entity. Analyzing is the taking things apart in the search for truth and recognizable relationships, which is what you would call decompositional analysis. And the question is, might we not get a better understanding of the creative process, and in particular this point of view phase, where we interpret if we adopt such notions of creative interpretive analysis? So that could give us some conceptual depth in that phase. Yeah. So, and of course, along the way, this notion of seeing as, how do we see the problem? What's our problem view? That's seeing as, playing through different ways of seeing as. And then another slide that, I don't know if we talked about it in length, where I just highlighted two notions. Paradoxes have been a driving force in the development of logic and philosophy throughout the history. And here I'd just like to highlight how this is treating problems as starting places for the creative process. And of course, that is also an idea we are very familiar with, that we start by exploring the problem space. We start with a problem. That's what gets the creative process going. And it's quite interesting, I believe, that in these very sort of special cases that we don't look at all too often, the creative history of philosophy or the creativity in logic, that there it seems to be a similar pattern. And then criteria for the use of concepts may come apart when we extend their application from normal cases. That's something you talked about. And here I just submit to you the parallel to our use of extreme uses. So we turn to extreme uses to gain insights, and I believe that's just doing the very same thing. So what I find quite interesting is that with these very detailed case studies, you describe principles and mechanisms that we're very familiar with. And I guess I'll just go back to the process model. I believe design thinking is very, very good at putting all these principles in a nutshell and teaching them. And I would see this process model actually confirmed also by these case studies that you described from philosophy, the history of philosophy and logic, where the same principles appear to be something very beneficial for creativity and creative outcomes. So I assume it's a nice thing to make them explicit and practicable. And now I move forward to the last slide. Or almost last slide. So that would be giving us instances, examples from the field of logic, which of course also for us as the Software Systems Engineering Institute strikes a chord, because we have many people who specialize in this mathematical or logical side of development. And given that you describe principles that we also know from design thinking, might we not build even further bridges, knowing that there are similar processes going on, similar paths and attempts of creativity and developing something that is novel and effective? So that's the last slide from my side. Would you kindly please come back, because now the floor is open towards all questions. Thank you.